In this video, we will talk about the efficient provision of public goods. So what we have done in the last video was to say, well, suppose each person in a game with two people, each person can decide how much to contribute to a public good. And obviously the contributions also affect how big or how the provision of that public good is. If both contribute a lot, there will be a lot of provision of that public good. If both contribute very little, there will be very little. And we have seen that in such a situation where the provision of the public good, how many units are provided, depends on the contribution, we have reaction functions that are negative. As in, people, the individual contribution negatively depends on the contribution of the other player. So if the other player contributes a lot, it's best for me to contribute little. It's best for me individually, and vice versa. And we have seen then that there is a Nash equilibrium whereby both best response functions overlap or cross, and basically no player has an incentive to deviate from the action they're taking, from the contribution they're making at that point. Yeah? So the question is now, is that actually Pareto efficient, or could we actually, through government action, improve welfare by solving the type of free rider problem that is inherent in this type of game, or generally in the provision of public goods? So what we want to do here is we want to first of all see to what extent a Pareto efficient solution actually exists and what that would look like for that very game. And then we want to see in a next step one possible way of getting there. Spoiler alert, it is very, very difficult. So there are a few instruments that we know work in theory, but implementing them in practice is very, very hard and depends very much on the society in which that public good should be provided, on people's willingness to pay for the public goods, the enforceability of these payments, and so on and so forth. So the devil is really in the detail. But before we go into the nitty-gritty, let's think first of how it could actually work. And let's also think, if we can solve this public goods problem even in theory, it tells us basically how big the pot of gold is. How to reach it then is a different question, but it's probably a good idea to first think, well, how big is it actually? Okay, so in the last video we talked about reaction functions, but we haven't really specified them in any way. Right? So here we revisit them, and we revisit them in a very simple manner. So what we assume here is that each person's total utility from consumption has two parts. The first part is the utility they get from consuming the public good. And we assume here two things. The first thing is that there is decreasing marginal utility. Or that's actually what we assume. So what we assume, first of all, is that the first derivative is positive, as in the more of the public good is provided, the better, but there is decreasing marginal utility. So what this means is the following. We've had this in one of the previous videos, namely that if you have the utility here and Q here, that you have something like that, whereby the slope of that curve decreases as we go along and as Q increases. So the idea here is that the first unit of the public good that is provided gives you a pretty high gain, but the next unit gives you a gain, but it's smaller. And then that additional gain from an additional unit gets smaller and smaller. That's what we assume here, which I believe is a very plausible assumption. Right? And so that's exactly what that formula that you can see here, that second derivative being negative, tells us. It tells us something about the curvature. Now, we could also alternatively graph the first derivative. So instead of having having utility on the x-axis or on the y-axis, we actually have the marginal utility u prime, and so the equivalent of the curve that you can see here is then, if we graph the first derivative, is some negative function. Okay, so it's some downward sloping curve. Okay, because as you can see here, as q gets bigger, the slope, so the first derivative of that curve, becomes flatter and flatter. And that's exactly what that curve tells us. And we will later use exactly that curve to think about what the optimal provision of that public good actually is. So then we're going to start with the so-called non-cooperative problem. So, which basically means that each agent just decides by themselves what is best for them. Right? And so for person A, that means they get the utility from the public good, and then they have the bit for the private good as well. And so they maximize that. In this case, we've substituted the budget constraint into the utility function up here, and so so this is the utility function that we're maximizing down here is really just a function of QA, person A's contribution, right? Because person A cannot, in this case, influence how much they earn. So YA, they cannot influence the price, and they can also not influence how much the other person contributes. Right? So if we take the first derivative of that utility function with respect to QA, what we get is so the derivative of this with respect to QA, which we simply denote here as UA prime Q, and that equals P. Okay, that's the first order condition we get here. Right? So what does this mean? It means that this first order condition implicitly defines what the optimal amount for that person is. Okay, so if we knew the exact utility function UHQ, we could simply then solve for the optimal amount of Q. Okay, so the person will choose a contribution that is exactly as high as it's needed for this equation to hold. So that was the non-cooperative choice, or the non-cooperative contribution to the public good. Now let's move to the optimal contribution from a social planner's perspective. So the idea is there is the social planner who wants to maximize the overall pie. Okay, so who decides basically for all agents simultaneously so as to maximize a social welfare function. And in this case, we choose a very simple utilitarian social welfare function. So we simply add up here the utility that person A gets plus and the utility that person B gets. And so what the social planner does is they maximize that function over the choice of QA and QB. So it's not that we let person A choose and person B choose, but we as the social planner or the social planner chooses for them. So again, what we do here is we substitute the budget constraint for each person into this equation. So for XA and XB, we replace that with, so here's the example, XA equals YA minus PQA. That's just the budget constraint substituted in here. Now, when we take the first derivative of this utility function with respect to QA, we arrive at that first order condition. Okay, and we assume an interior solution, so then we just set this at the optimum equal to 0. How do we get there? Well, it's very simple. We have to take the first derivative of this, of UA, which is a function of QA plus QB, with respect to QA, plus, well, YA doesn't depend on QA, so it's actually, apologies, it's actually minus P plus, and I apologize here, there is a typo, so this should be UB. Okay, right, so we have here, it's getting a bit messy now, but we have here the utility for person A, and here we have the utility for person B. So we continue with our derivative here, which is that we take the first derivative of UB, which is again a function of both people's contributions, with respect to QA, and that's it. Okay, and then what we've shown here is exactly what the first order condition is. The nice thing is that when we take the same derivative with respect to QB, the exact same thing comes out. Okay, and now we can look at that first order condition and we can see that it looks different from what we have in the non-cooperative solution. Okay, so the social planner again factors in the utility of both members of that society, and so maximizes welfare over both these people's contributions to the public good. And as such, that social planner also factors in, from the perspective of one person, also factors in that the other person's utility. Okay, whereas if I decide by myself what's optimal for me, I don't factor in the other person's utility. And you can see this then in the difference in the first order conditions. Remember, in the market solution, which is what we had earlier, the non-cooperative solution, the first order condition looked different. It looked like this, right? So the utility of person B did not play a role here at all. And so what you can guess here is that the contribution that is chosen here and the contribution that is chosen here are very different. Okay, so in the social planner will choose a different level of public goods provision compared to each person would choose on their own. And so from that derivation, we actually get a rule for the optimal provision of a public good. And optimal means here efficient. So that's the Pareto efficient provision of the public good. And this equation here is a form of what's called Samuelson's rule, named after the famous economist Paul Samuelson. And it simply tells us that the marginal social benefit of the public good, so the marginal benefit that all the members in the society jointly get, equals the marginal cost of providing one more unit of the public good. So if you remember that diagram with the demand for the public good and the supply, at the point where those two lines cross, that's exactly the point that is defined by this equation, by Samuelson's rule. Okay? And so the idea here is basically like on in the very basic private goods literature or the private goods models, which is that the marginal benefit of another unit of Q must equate its cost. Right? That's the equilibrium. That's the equivalent of supply equals demand. However, what is different here is what goes into the marginal benefit. And it's not the marginal benefit of a single consumer, but it's the marginal benefit of the entire society. Right? So of all the utilities of all the people taken together. Does the Samuelson rule always look like that? No, because the social welfare function here is a very special one. It's a utilitarian one. It could be a Rawlsian one, and it would look very different. It could be something in between Rawlsian and utilitarian. It would also look different. Right? So, but for simplicity, we chose here a utilitarian social planner, which is arguably the easiest to deal with because you just add up the utilities. Okay, so here is again the comparison, and what we do is we're gonna call the optimal Q, the optimal amount of the public good that is chosen by the social planner, we call that Q opt. And we call the privately optimal amount of the public good, we call that Q star, and that's basically what we did in the last video. That was what comes out when we look at people's mutual best responses to the other person's actions. That's the Nash equilibrium that would come out of that. And what comes out of that is private marginal benefit equals private marginal cost, whereas in the social planner problem, what comes out as the solution is social marginal benefit equals social marginal cost. Now, to make the two of them comparable, what we're going to do is here, we're simply going to add the two marginal utilities. We're going to add them up for the market. Okay, because then we have for both the market solution and the social planner solution, we have on the left-hand side the marginal utility person A gets from the provision of the public good plus the marginal utility that person B gets, and then on the right-hand side we have the marginal cost that differs in either case. So, is the social planners the optimal amount chosen by the social planner different, and is it bigger than the optimal amount of the public good chosen in a non-cooperative solution? And the answer is very, very clearly yes. Okay, so here we graph the marginal utility against the amount of the public goods provision. And we can see here that, well, at the socially optimal level, the social marginal benefit equals P. Whereas in the market solution, as in the non-cooperative solution, the social marginal benefit, which is what you can see here, equals 2P. Okay? And now we know that the marginal utility decreases in Q. Okay, so that curve is downward sloping. So if we know that at the amount that is chosen non-cooperatively, that the marginal benefit is higher, it must mean that amount is lower, the amount provided of the public good, than what the social planner chooses. Okay, so in a nutshell, when you have a non-cooperative solution whereby each person just factors in what the other person does, but each person equates or chooses in such a way to contribute to the public good that their private marginal benefit equals their private marginal cost, that together will lead to a lower provision of the public good than what is socially optimal, than what is Pareto efficient. Right? So the social planner will choose a much higher level of the public good.